Uh, okay, good afternoon, everybody. It is our pleasure to invite Dr. Pulgar to give us a seminar about power system control. So Dr. Pulgar was born in Los Angeles, Chile. He received his bachelor and master degrees in electrical engineering from the University of Conception. Is that right? Is my pronunciation right?
Yeah, very close.
Okay, all right, Chile in 2001 and 2003 respectively, and his PhD degree in electrical engineering from the University of Illinois at Urbana-Champaign in 2010. He became a Fulbrighter in 2006. He held academic positions at Federico Santa Maria Technical University, Chile, from 2001 and 2014. He's currently an assistant professor at UTK, and he's a member of IEEE and also CURENT. In 2021, he was a recipient of prestigious NSF Career Award to work on discrete control actions for power system dynamic performance enhancement. His main research areas are power system dynamics, energy storage systems, and renewable power generation. With that, the stage is yours, Dr. Pulgar.
Thank you so much. So I will talk today basically about the research we have been doing in the last years, a summary, and I will focus on one of the first finding we got in our work, which is related to reinforcing the power grid for to improve the dynamic performance. So, oops, can you still see my screen?
Yes, we can.
Thank you. So I will have a very short introduction, and then I will talk about the power system dynamic enhancement, which are basically the research achievement we have done in the last years, 6-7 years. So all the work that I am going to present here come from our group, and this cannot be done without the help of my students, and these are my former students. I have Yashwin. I was never able to pronounce her name very well, but she was my first student, and she got a PhD with me. And then we have Horacio. He also got a PhD, and the last two guys is Jonathan and Michael. They both got a master's degree with me. And my current student now, we have Francisco, Timothy, and Sebastian that are working with me on this aspect. So introduction, I want to make it very brief introduction, and I don't want to bore you with very basic stuff. So the first thing, everything started long time ago with the development of the AC and DC electrical system, and we have this fight with Edison and Tesla, and at that time we have just isolated development of the electrical network to supply electricity to individual towns, but after a while then the AC system was more efficient and effective, low cost, and we realized that the interconnection of these was going to improve the reliability of the system. And then after several decades, we have what we know today. So it's a very large network with a huge number of component generators. We have consumers, lines, transformer, and many other equipment. And these are one of the largest engineered system created by humankind. So it's very large. It's hard to sometimes to understand the behaviors and to represent, to model this system. Not because it's so large, but also because you have uncertainty, you have energy consumption that change. And even though today we can predict that with high accuracy, but still that's something we need to tackle every day. And now we have renewable generation, which is more volatile and is harder to predict. And of course, failures. You have failures sometimes induced by human error, sometimes by weather conditions, and those are hard to anticipate when they happen. So, and not only that, but it's also complex. It's large, uncertain, and complex. And one of the things, our system is a synchronized system. So whenever something happens in one part of the country, that can affect a region that is even very far away, because it's all synchronized. So we're dealing with a very complex system. For over a century, we have the system that we understood, and like with this picture, but many people believe that this was kind of an old engineering field, and we started getting less people interested in this because it was the same all the time. So students were not interested in pursuing a PhD degree in this field because there was nothing exciting here. But something happened, and what happened was in 2003 when we have a huge blackout. And in this blackout, it was in summer, a lot of consumption in the country, but unexpectedly the system just collapsed. So more than 50 million people were without electricity that day, very hot day. In New York City, people got trapped in the city, could not escape from the island, a lot of chaos. This was just 2 years after the terrorist attack to the country. So people were very concerned and panicking about the situation. In some part, the electricity didn't come back even in 2 days after the blackout. So that was very, very catastrophic. A lot of concern, but also economical consequence of this. You know, a lot of losses, economical losses as well. So after this, there was a big change and a lot of people got interested. We realized that the grid was kind of outdated and need to add more new technology to make it better, to make it more reliable. So from this point and on, we started seeing new things that were being proposed to improve the operation of the grid. So one of them, of course, is the renewable energy. We started being more aggressive with the development of renewable energy and how we can change a system that was basically based on thermal power plants, plants based on fossil fuel mainly, which are very slow to respond, and they have a lot of energy involved in their operation, in their rotation. And when something there is a disturbance in the system, there is some problem, these machines will start responding very slowly, and it's something very hard to handle those dynamic operation. So I have here a way to describe this, and this is through the Sankey diagram. And this is a diagram from 2010 that describes more or less how the energy production and consumption in the whole country during that year. The data here is presented in trillion of BTU, but these trillion of BTU can be expressed also in quats. In this case, 98,000 trillion BTU is equal to 98 quats. So we can talk about quats here. In this diagram, you can see all the primary energy sources that we have and how they are transformed and used in different sectors: residential, commercial, industrial, transportation. And also we see here how much of that energy that we have, energy flow, how much is actually used for services and how much is lost. Most of this rejected energy is basically is heat that dissipate in the atmosphere and we cannot recover. And that is actually a sign of a thermal process, a thermal system. So from this picture alone, we can see how our grid is mainly based on thermal power plants. This is the whole picture of all the energy in the country, but this part right here, just consider the power grid. So in the power grid, you see there is one of the primary energies, big one, is coal power plant. Very cheap, but very pollutant, and that was the most significant in 2010. And then you have natural gas, which is fossil fuel too. You have nuclear power, which is different, but also it's a thermal process. So these power plants are very slow as well. And then you have the other types that are not thermal, like hydropower generation. That's very different, very robust, very fast to respond. But we don't have many resources for this in the country. And then at that year, you started seeing new development like wind energy and solar. So I want you to look at this and see how this changed in the 2018. Okay, and this is the situation. So there is a big reduction in the coal power plant here, and we started seeing an increase in the renewable energy related to wind and solar, and the same thing will happen in 2010 with a further increase in wind and solar. So the system has changed importantly. Still, sadly, I would say, if we look at this part of the plot, this is the power grid. The orange part is the energy actually produced as electricity that is sent to all these sectors, residential, commercial, industrial, and the gray part is a rejected energy. If we calculate how much is the percentage of this orange part with respect to the total energy, I calculate this value, it is still 34.8%, which means even though we have wind and solar, still the system is mainly dominated by thermal power plant, because we see that a thermal power plant typically will have an efficiency around 30%, and we're not very far away from that. So even though we're increasing wind energy and solar, still the system is dominated by this slow power plant thermal process, and whenever there is an incidence in the system, we need to tackle all the problems that we might generate by this incident. And by the way, if we compare this with the case in 2010, I calculated the percentage. At that time, the efficiency here in the power grid was 32.5%. So in 2010, 32.5%, and in 2020, 34.8%. There is an increase, but it's still not significant. So I don't know how long it will take, but we will have to deal with a totally different system if the renewable energy will keep increasing to higher levels. And then this percentage that I'm talking to you about efficiency will start increasing as well. But so far, I would say that we still need to have high dependency on this thermal power plant and all the issues that we well known about the operation, dynamic operation on these machines. So the grid is moving to more renewable energy, but it seems that the rate is not very fast, but it's still moving. But still, we need to deal with this dynamic issue related with conventional power plant generators. So in my research group, our efforts has been to developing new concepts or new strategies that can improve the dynamic performance of the power grid when the system is subject to disturbances. So one of the first work that we did, and we got a very important result, was related with the reinforcement. So if you have the power grid, how can we reinforce the grid with new actuators and controllers in different locations? So the dynamic, the power system is more robust, can take some disturbance without degrading the stability of the system. So this reinforcement, this problem was basically related to the idea of, is there any way we can determine an optimal location to decide in advance, more in a planning stage? We can decide where we should put these actuators and controllers so the grid is more robust. So that's a hard question, because even though this look like a planning process, it is in a way, but the goal, the objective is dynamic, and that is hard. How you handle something that is long-term, like planning, with an outcome that is just at the second scale, very fast, is the dynamic response. So that's something that has never been done before, and that was very challenging. But we had an idea, and we worked on that idea. And the idea was to find some function, some index that can hopefully can show us where we should reinforce the grid. Whether, for example, here in this graphical description, I have a grid, and the idea is on top of this grid to have some sort of index function that can show us whether would be optimal to deploy a control actuator or not. So for example, here, if this is accurate, this function would tell us that actually at this bus, you have a generator, but actually that's the best place to deploy a control actuator, because that will improve the dynamics in an optimal way. But also at the same time, there are places in which this will have a negative effect. If you put a control actuator in this part, then the dynamic will be worse. So that's we were looking at for a function that can describe this behavior. So as I said before in the introduction, the system still is highly dominated by conventional power plant. And one of the main dynamics here that we have to deal with when there are disturbances are oscillation, electromechanical oscillation. So the goal is to define this location so the controller will have an optimal improvement in the dynamics. And the goal here is going to be to minimize the oscillation in the system. So how we started, and probably I will spend a little bit more time on this, and in the other research that we have done, I will go more quickly, but I would like to spend more on this, and I want to show you with us a simple case the meaning of this result we obtain. So we will start with the idea that you have a model for the power system, and then we will linearize it. And this is good at the beginning as an assumption, but then this was tested in any condition, not in a linearized fashion. Everything was considered a full nonlinear model with different controllers, and it was simulated in larger scale to validate the result. But at the beginning, we needed something simple to develop some analytical condition that can lead us to find a function that can help to identify this optimal location for control actuators. So we start with this linear representation here. So you have the state equation, you have the vector state x, and you have this linear representation. We are going to consider you have control input. This is going to be the input that come from the controllers. And we will consider the system initially in open loop. So we don't have any controller yet designed, and we want to explore how the location can have an impact on the dynamic response. So this is going to be in time domain. The first thing we do, we transform this to the frequency domain using the Laplace transformation. And after this, all these differential equations become algebraic, and then we can do some algebraic manipulation on this side. Here, for example, we can send this to the other side and factorize by the vector x, s, and we obtain this relationship. And then we can multiply from the left by the inverse of this matrix, and then we have an explicit expression for the state variables, all in frequency domain. So when we have this, then we can multiply this by the matrix C, and you have the vector of output. And here it requires that this matrix, of course, need to be invertible. And then by a similarity transformation, we can transform this matrix A, and we can use diagonal matrix lambda that contain the eigenvalues of the system. And for that, we need to use the right eigenvector and left eigenvector. So we can prove that from this relationship is equivalent to this. The simplicity of this equation is that this matrix here that we're trying to get the inverse is actually diagonal. So all the off-diagonal terms are 0, and in the diagonal term, basically, you will have terms that are 1 over s minus the eigenvalue at each different location. So because this is that diagonal, then what we can show is actually this is nothing else than this sum of term in which we will have each eigenvalue represented individually. In the numerator, we will have this term that depend on the left and right eigenvectors associated to that eigenvalue lambda j, and depend on the coefficient of the matrix B and C that depend on the grid. The coefficient of B will depend on where actually your control actuator is, and that is related to the location. So if you put a controller somewhere else, then the coefficient of this B will change. So somehow that location concept is included in this matrix C. And the same for measurement. We will assume that at the beginning that you have a local controller. So you take local measurement and you measure exactly in the place where you are injecting. So by that also this matrix C will depend on the location. B and C will depend on the location. So given a controller, you will have this term, and this is going to be associated with the eigenvalue lambda j. And this term on top is called the residue. So if you have a high residue, that means that this eigenvalue, that mode, actually is going to be significant in the behavior of the system. And of course, this will be repeated for all the eigenvalues you have in the system. So here I am making a distinction to start with, to obtain a relationship. And the assumption here is that there is one eigenvalue that is the most dominant one. So those dominant eigenvalues are those that have a very slow behavior and they are sustained in time. If we plot them in the complex plane, these eigenvalues are very close to the imaginary axis. So I'm going to separate that term, and this is going to be related to that very dominant eigenvalue, and this is going to be the residue of that dominant eigenvalue. And here we have the rest. We will assume that these are fast, they are stable, they die out very quickly, but this is the one that is sustained and will dominate the behavior. So with that, we want to see how that can be modified, can be controlled now if we put a controller somewhere in the system. And for that, we started using this radial system. Very simple. You have two machines, you have two transformers and a line. At the beginning, I'm not going to use any controller yet, but I'm going to define the bus 3, and this bus 3 actually can be located anywhere between the bus 2 and 3. Yeah, and I will later add a controller in bus 3, and we will see how the dynamic of the system will change when the controller is closer to bus 2 or closer to bus 4 or closer to the middle part. And we will start like understanding the impact of the location of that control actuator. To start with, we start with a classical model for the machine. Very simple. You have an induced voltage in series with a reactance for the generator. This transformer and line are going to be represented by reactances as well. So the equivalence system, circuit for this system is the one that we have here. Because you have a reactance in the generator and in the transformer, at this point, at that bus 2, we will have some reactance. As I have just a reactant in the system, we have a total reactance that is X, and I will use a coefficient alpha to indicate at what point along this line we're located. So alpha will have a minimum value because we need to consider the reactance of the generator and the transformer. But if I start increasing alpha, I will move along this line. At some point, I will be in the middle, and I will keep increasing alpha until I am at bus 4. And here we will have an alpha that is maximum because you have a reactance in the transformer and in this motor. This is a synchronous motor, this is a synchronous generator. So that's the system we will use. So as I said, we're using a classical model. So basically you have a swim equation for the generator and the motor. So you have mechanical power driving the behavior of this, but in this case, what drives the behavior is electrical power because it's a motor. The changes in the angle are defined by this, the speed difference with respect to the reference, which is the nominal speed. And omega 1 and omega 2 are the speed of the generator and motor in per unit. So that's the classical model. When we do this, we have network equation that as we don't have any controller, we can just work with this system, but we need to write down the network equation because what we're looking for is to get some description of bus 3. Bus 3, initially, we don't have any controller, but later on, we will add a controller, and we want to see the impact of that controller on the dynamics. So I need to know what happened to the voltage and the angle in that bus 3. As I am dealing with oscillations, actually the most significant variable that I need in bus 3 is the angle and the frequency in bus 3. And here, initially, we have some issue. So the issue was, how do I determine the frequency in bus 3? So at that time, actually, we didn't have any clarity on what to do. And so what we did at that time, we tried to develop some simplified equation from which we can determine the frequency in bus 3. Because this is a PV bus, a PQ bus, so it's a passive load. We don't have any injection whatsoever. So in the power flow equation here, we just know voltage and angle, but we don't know the speed, the frequency. We do know the frequency in the generator in the motor because it's included in the dynamic model, but we do not have the frequency or speed in bus 3 because it's a PQ bus. So what we're going to do, we're going to use the algebraic equation for the voltage in bus 3, which is basically the voltage from the generator minus the voltage drop in the first part of the line, this part right here. So we take the voltage at the generator, internal voltage, and we subtract this voltage drop in this impedance, and then we have the voltage at bus 3. And that's the equation we have here. But this is troublesome because you have voltage, and all that we need at the moment is to determine the angle. So the trick here is to work with this equation. So one thing that we do in this voltage equation, we multiply by exponential of negative j theta in the this equation, and then we obtain this. And then what we can do, we can take the imaginary part of this. By taking the imaginary part, this becomes 0, and we get rid of the voltage. So we obtain an equation, exactly what we were looking, an equation that determines the angle at that bus tree. Because we want to have something analytical, we make also the assumption that the voltage angle difference, this one here and here, are small enough. So sine of delta 1 minus theta can be expressed just as delta 1 minus theta, as here. And the same thing with this. This sine of this angle difference is just the angle difference. So with that, we obtain a linear equation. I can isolate for delta. I can factorize by theta and send it to the other side of the equation, and we get this term. And then I divide this term by this, and I get an expression for theta. So what we obtain here is that theta, the angle in bus 3, is a linear combination of the angle of the generator and the motor, linear combination. Of course, if these assumptions are satisfied, this will be somehow accurate. Now that I have the angle theta, what I can do, I can take the derivative of that angle theta. We said theta is a linear combination of delta 1 and delta 2. So when I take the derivative, these remain as a constant, and basically you have the derivative of delta 1 in time and derivative of delta 2 in time. We can replace from the classical model the equation we have for the derivative of the angle, and you have this term, and you have this term here. Then we can factorize by omega s. And then I can separate the term here for omega 1, omega 2, and this constant value that will show up. The final result is this equation 1. So the derivative of the angle is equal to omega s by this expression. So finally, as the derivative of the angle is equal to this expression, conceptually we know this, we can isolate for omega, and we realize that omega is nothing else than this term inside, which is the equation 2. So finally, we were able to, in this simple model, to obtain an expression for the frequency in per unit in bus 3. Now, our initial idea was optimal location somehow needed to be related to the inertia in the system. But the inertia is something hard to describe, because you have inertia in one generator that might be some value, and inertia in the motor, and they might be very different. But along that line, the equivalent inertia that you see at a bus 3, for example, will be some combination of those. And that's what we call the distribution of inertia. How that inertia that are in this generator is distributed along the grid. And then when you're in a PQ bus, you see some equivalent inertia at that point. So we were looking for that. And we have the hypothesis that the optimal location were related to those places in the grid in which you have a less distribution of inertia. So the inertia is weak, it's low at that point, and therefore those are the best places to deploy this control actuator. That was the original idea, but we needed to obtain some theory and validate that. So one way to do this, we thought, well, to determine this, maybe we need to determine the center of inertia. The center of inertia should be the point in which you see the highest concentration of inertia in the system. And physically, if you have the power grid, physically it should be a point in the system in which the angle do not change much when the system is under disturbance. On the contrary, if you have a point that change a lot under a disturbance, that means that that point has a weak inertia and is very far away from the center of inertia. So the first thing was to determine what is the center of inertia. So as we have a simple system with simple representation, we look for that by solving this optimization problem. We are looking for the alpha in this linear system that will minimize the changes in the angle in the system. So we solved this optimization problem, and the solution we obtained was number 4. So that's actually the center of alpha, in which the center of inertia will be located for this radial system. When we pick this alpha of the center of inertia, we plug that here into this equation 2, and then we obtain the frequency in that center of inertia. And this is the well-known equation that probably you have used for the speed of the center of inertia, which is basically inertia-weighted frequency among all the machines in the system. So this was known at that point, but equation 4 was unknown. We have numerically a frequency in the center of inertia, but we didn't know where the center of inertia was actually located. Now, with this derivation, then for this system, we know that the center of inertia will be located in alpha star, given by equation 4. Okay, so we have an idea now. We have a bus 3 that can be located anywhere between bus 2 and 4, and we have a location for a bus 3 that will actually be at the center of inertia. So the hypothesis is, if you put the control actuator at the center of inertia, because it will have the highest concentration of inertia in the system, then the control actuator will not perform as well as you want, because that point will not have a lot of changes in the angle, in the frequency, and therefore your control logic will not provide much power to dump the oscillation. So we're going to put the controller, and we're going to change the bus 3 between bus 2 and 4 and see what is the result. So I will move a little bit quicker here. So we have the classical model still for the 2 machines. And now, because we're putting the controller that is injecting power in bus 3, we need to add the algebraic equation that relate this power with the angles in the machine. And that is given by these 2 equations. We're going to assume here that the reactive power from this control actuator is 0. So this P will be will change based on this control logic. So we do that because this is still a linear system. The only thing that we will do at this point, because we want to work with an open loop system, the control logic will not be implemented, but just the power. But we will have the input that will be the power, and the output of our system is going to be the frequency in bus 3 that we already determined. And by looking at the output and input, we can determine actually which location will be more effective. So the first thing, because this is linear, we need to eliminate the algebraic equation, and we do that by applying the Cron reduction. After you eliminate the equation, then you have a system matrix in which you calculate the eigenvalues. And after a lot of calculation for this system, then we prove that the eigenvalue for that system is given by equation 6, and the right and left eigenvectors are given by equation 7. So we have a description of the eigenvalues and the eigenvectors. So if we go to the beginning, where we have the transfer function of the system, we're going to look at the situation. So you have the dominant eigenvalue, and you have an right eigenvector related to the dominant eigenvalue, a left eigenvectors, and you have matrices C and B that are related to the location. So we will determine the residue of this. Because the residue is going to be the one, an indication is a sensitivity actually proportional to the sensitivity. It tells you how much the eigenvalue will change with the gain of a controller you can put in bus 3. So we will look at the residue, and when we change the location of bus 3, we will see which location will lead to the highest residue, because that's the one that will have a higher impact on the eigenvalue. And therefore, we can deploy a control actuator that can make the system more stable. So from this point and on, the goal is to find an expression for the residue. So we do that. We have all the analytical expression. We come up with equation 9, but then we can do some manipulation here, and the residue can be expressed in this fashion. This looks much better because now in this residue, we see a difference between the alpha, the location of bus 3, and the location of the center of inertia, which is fixed. So here you have an indication of how far away you are from the center of inertia. And at the bottom, you see that you have a voltage difference here, and actually all these terms can be simplified. These should be small enough with respect to E1, so all the denominator can be just E1 prime squared. So we have an approximate value expression for the residue. And the residue, as you see, is a convex equation that is centered in the center of inertia. So if I move away from the center of inertia, then the residue will increase. So here we have the validation of the hypothesis. We have an idea, but we have to do all this work to validate and say, yes, this location problem is actually can be expressed in terms of the center of inertia. And the distribution of inertia, basically, how is my inertia compared with the center of inertia of the system? And if you are far away from that center of inertia, then your control actuator should perform more effectively if you are closer to the center of inertia. So from here, you got an idea of how you can deploy these control actuators in the system. So I have a plot here because then for this small system, I simulated in Power Factory, and I consider a nonlinear model for the machines, and I put exciter and governors, and we model all with all the details possible to validate this expression, and the result was outstanding. The approximation is the segmented line, and it's very close to the actual result that we obtained from the simulation. So from here, we got the validation of our test, and from here we needed to see whether this would work well in a realistic system. So in a realistic system, then we needed to define some numerical ways to determine where's your center of inertia and how away you are from that. So we define the frequency of the center of inertia is the standard equation 12. You have done this, some of you have done this probably. So this is how we had been doing this for so long. But then we're going to take the frequency. If you have a control actuator in bus K, you want to measure that frequency with respect to the frequency of the center of inertia and calculate this error in time. In that way, you have an index that will tell you how far away you are from the center of inertia. And then we normalize this index to have something standardized. And by looking at the lowest index for all the buses in the system, the one that has the lowest index, that's going to be the location of the center of inertia. Okay, so this index, numerical index, will be an indication of how away you are from the center of inertia and how effective a controller would be in that location. So we're looking for the highest value of IVI. So we apply this where the system is radial. So we needed to apply this in a system that might look like radial, and that's my country. Very long and thin country. So the system are very long in kind of radial. So that's the description of the system, but let me move a little bit farther. And And this system has this dominant eigenvalue that is plotted here, very significant and dominant eigenvalue. It has a very low damping ratio and frequency. And we tested the idea. We deploy control actuators in different buses in the system, and we calculate this index, and we verify whether that was a good place to deploy this control actuator, and we validated the result. So the center of inertia should be close to this area, but if you move away, then the control actuator will be more effective. So we validate that by full nonlinear simulation, and we obtain very positive result. Then we tried to apply this to other systems, but we realized that inertia distribution was insufficient to solve this problem in mesh network. So the problem was more complicated because of the eigenvalues, and the oscillation mode were more complex. So our approach then was to use machine learning to identify actually if the distribution of inertia is not enough, what other indices we need to pick to determine what could be a good location. So we collect this data, we define 36 different features, characteristic of at a given bus to determine what this best indices would be to solve this problem. The issue with that was we have 37 actually parameters, and that was hard to track a large number. So we needed to discard those features that were not that relevant. So we use least absolute shrinkage and selection operator to determine which are actually the most significant one. And by solving this problem, we got this result. We have to move the parameter alpha from very small values. When you have a very small value, actually all the parameters in your problem are relevant. And this will lead to some accuracy in your model to determine whether that location is optimal or not. But as you increase the value of lambda, the parameter in this formulation, then some parameters start being discarded. Some of them become less dominant, while others still remain there, and they're the most significant one. So the very last feature that remain in this problem is actually the distribution of inertia. So we were not off actually in our intuition at the beginning. Distribution of inertia is there, can help you to determine a location, but in very complex mesh network is not enough. So you need other features. So there are features like impedance distribution index or distance to the fault location that can also help. We use this point here, with this alpha, we realize we still have a good accuracy in our prediction, and we obtain this model, and by using all these features, which is more manageable, we were able to identify in a mesh network the optimal location. Well, I believe that took most of my time, so I will go very quickly over these two parts. So this is another work that we started working on this a few years ago, which has to do with the coordination of controllers. You have controllers, and when you design a controller, most of the time you need to make assumptions. You need to make assumption about what are the dominant modes, or another assumption you have to make, if not, is implicit in what you do, is that you need to assume that that mode is going to be excited. Some disturbance might not excite that mode, or it might excite the mode very little, not significantly. Therefore, if you have a controller designed for that mode, the mode is not there. So the controller will have some action, but it's likely that that action from the controller will make things worse because it was designed to damp an oscillation mode that is not there. So we realized that actually we need some sort of coordination when you have this controller, because the excitation of mode is something that we cannot anticipate, that depend on the fault disturbance in the system, and this can be anywhere in the system. So what we did, we developed the theory, did some analytical derivation, and we proposed a scheme based on sensitivities. We have the full model of the system, and through eigenvalue sensitivity with the controller gains, we were able to decide, depending on if that sensitivity was positive or negative, we were able to determine whether we should turn on or turn off a controller. So the scheme was basically, the logic was, depending on these sensitivities, then you send a signal to this controller to activate or deactivate. So we test this in the WEG system. You have 179 buses here and several generators, and we have controllers, and we assume that these controllers came from energy storage devices, and we enable some controllers in these 4 energy storage, and these 3 were disabled. But in that system, you have a disturbance in this bus, and then you determine the sensitivities, and you realize that the control actuator here in this controller that is off actually is the most sensitive and need to be turned on. So by doing that, you can see the improvement in the oscillation. The system responds better when you turn on that controller. But there are other cases that are more complicated. You may think, well, you need to put the controller, activate the controller that are closer to the fault, but that's not always the case. In this case, we apply a disturbance here in the north part of the system, and based on our calculation, we determine actually that this controller that is on is the most sensitive but need to be turned off. And by doing that, then again, we improve the performance of the system. So with this, there are some drawbacks in this. Even though it worked, we prove that this scheme, if we know these sensitivities, should work. But the drawback is this calculation are time consuming. And not only that, these sensitivities are going to be dependent on the operational condition, loading levels, unit commitment, and topological changes too. If you have a fault, you might have a line outage, and this sensitivity might change. So the solution to that, and this is something we're working right now, we're proposing a neural network, deep reinforcement learning, to learn and to base on all these characteristics, changes, operational changes, changes in the topology, and the status of the controllers, and how much significant is the oscillation. We're trying to learn and to come up with a logic to determine what is the optimal on and off of all these controllers that would improve the dynamic operation in the system. The last part, very briefly again, hopefully I can do this faster, is the discrete control. And this is the last work we started just last year. And this has to do with discrete control. But why? Why do we need discrete controls in the system? Because all the controls we have are continuous. Well, the answer, there must be several arguments for this. And one is that the grid need more controllers for a robust and stable operation. The system is changing, and we expect that the renewable energy will keep increasing, and the dynamic behavior in the system can become very critical, especially this oscillation or frequency excursion in the system might become more critical. So is there anything we can do to add more controllers? And then if you need to add more controllers, where you are going to get the energy from these controllers? And The thing is, there are new technologies that have increased our participation in the grid, like energy storage, solar power, but unfortunately, especially solar power, they have very limited capability. Solar power operated at full power, and if you are at full power, then you don't have much room to control and modulate that power. So we thought, is there any way that we can decrease that power from the solar panel and still have an improve in the dynamic operation? And from there, we came up with the justification for discrete control. If we can provide discrete changes in the power, then we might be able to put controllers in solar panels or other components. So the idea is basically related to orbit, and by applying a discrete change, basically we're going to change the orbit of oscillation in the system, and we want to apply that change in a way that the new orbits, for example, in this case, the system starts from the equilibrium point, and there is a short circuit, and the state variable will deviate until the short circuit is clear. Let's assume for a moment that this is a harmonic oscillator, there is no damping. So the system will be trapped in this sustained oscillation forever. Now that the short circuit is clear, the idea is, can we change discretely the power in some of this controller so the equilibrium point of the oscillation is shifted? And yes, we can do that. When we change discretely the power from these controllers, then the oscillation will be shifted, and you will have an orbit center in another equilibrium point. But for this one, the key is that the equilibrium point lie along the trajectory of this shifted path. So when the fault is clear and the system is oscillating, I can switch the power in some components. I will change the trajectory, but when the trajectory passed from the equilibrium point, I can switch that back and leave the system there, and theoretically that should eliminate an oscillation. So for a small system and some assumption we made, we already obtained a switching function that we can be applied that, and that has been validated in a system like the 3-bus, 9-bus system. And here you have the situation, you have a short circuit, the system oscillates at the beginning, but then you apply the discrete control here, you switch on the variable, you change the power, but then you change the power back and you go back to the original behavior of the system. And as you can see, the oscillation is significantly reduced. Well, that's the presentation for today, and these are some reference to our work. And I acknowledge the support from the National Science Foundation and the Department of Energy and the CURENT program for all the support during these years. Is there any question?
Thank you, Dr. Pulgar.
Okay.
Question time. Maybe we have 1 minute left for a quick question.
I guess I have a question.
Please.
So if you are, I believe this is on the third part, if you're trying to find the optimal location for a controller using machine learning, I guess what variable are you trying to solve for here?
So the idea were two types. You know, there are operational variables and features, operational features and physical features. A physical feature is like inertia. You have some power plan and that doesn't change over time unless you have unit commitment. Another physical feature can be the topology of your grid. It will change sometimes if you have line outage. The impedance, those kind of physical features. But also you have operational features like loading levels. So if the decision is mostly based on physical feature, this is something you can anticipate. and you can plan in advance. So if you have a few options to locate these control actuators, then you can pick those locations with this physical attribute that will improve the most the dynamic performance in the system. If these are more based on operational features, then that's something not very useful, because operational things will be changing over the time, and that will be hard to anticipate. In this work, we found several physical features that can be used when you deploy this control actuator. So you will have some positive impact on the dynamic performance of the system if you follow this guidance.
All right, thank you.
You're welcome.
Okay, with that, let's thank Dr. Pulgar again.
Thank you so much.
Then we can wrap up the seminar today. Thank you.
Yes, thank you. Bye-bye.
Bye.
Thank you.